Okay, hello everyone. Welcome to the session. So, today we will be covering week 10 theory. Technically, in week 10, we do not have any coding part. So, in both the session, today and on Wednesday, we will be covering just the theoretical part only. Today, I will be discussing the architecture of the transformer from the Attention is All You Need paper. Okay, and on Wednesday, Puneet will be covering I think the last two lectures of the week 10 that covers how does the modern LLM thinks part. Okay, so that's the plan for week 10. Before starting that, anyone has any doubt?
So one thing I can ask, like we are doing this all practical stuffs, like the CNN parts and all. So how
Hmm?
can we do this on a, production level? If I want to do some apps on it, how can I do a production level work? If you give some
Uh,
idea.
okay, that part will technically be covered in the MLOps, like how you deploy your models. Okay, so that stage will not be covered in our course. Some part of it you can say is you can deploy on Hugging Face. Okay, but for a full production level, that much technicality will be covered in MLOps course. So that's a totally different stream.
Like in the degree level courses.
Yeah, it's a degree level course.
Okay, fine, understood.
Yeah. Yeah. Anything else? Uh, okay, I hope my screen is visible. Uh, okay, right. Showing. Yeah, perfect. Hmm. So let's start with the revolution in generative AI field. So things started around 2018, like approximately 9-10 years before today. Okay, when Google introduced first transformer model, BERT. Okay, that was basically model for the text related area, mostly related to NLP. Then following year, OpenAI released his GPT-2 model, which was for large scale text generation. Following that, GPT-3 was released by OpenAI for few shot learning. Few shot learning here is basically one kind of fine tuning techniques. So there's zero shot, there's few shot. So zero shot means you are not using any prompts to fine tune your model. Few shot means you are using some prompts, and based on that prompt, what should the ideal response to be to fine tune your model. So that's the few shot learning. Okay, that was done to fine tune the GPT-3 model, which has approximately 175 billion parameters. So quite large number of parameters were used to train GPT-3 model. Following that year, in 2021, DALI and Codex was released for code generation and image generation from text to image. And around the year 2022, with some small modification, not small, but some modification in GPT-3 model, they call it GPT 3.5 internally. They released ChatGPT, which was the game-changing part and which kind of revolutionized AI. And then following that year, GPT-4 was released by OpenAI, Claude was released by Anthropic, Gemini was released by Google. Then now GPT-5 is also released. Okay. So all these different models that we see nowadays, they all follow one main architecture block that was the transformer block that came on 2017 paper Attention is All You Need, that was released by around 8 scholars from Google Brain Lab. Okay, and this was the most important building block for each of the models that we see today. For any LLM that you see, they use the basic idea of this transformer block that was introduced in this paper, and that's what we will be seeing today. The fundamental idea for this that was attention is what we have already covered in week 9. Okay, now we are just using that attention idea and just describing the architecture that they used for this paper. Okay, so the motivation, like why we move to the transformer, is we have already defined through the example that I also took before. again, if I take the same example that suppose we have these two sentences. First one, that the chicken did not cross the road because it was too tired. Second one, that the chicken did not cross the road because uh, if it was too wide. Okay, the if should not be here, but ignore that. But the idea is in the first sentence, the it here was referring to what? Chicken. While in the same sentence, the same it was referring to the road. Okay, so depending upon the company that my word keeps, its meaning changes, its semantic changes. Okay, and another example for it be, if I have the sentence, I went to the bank to fetch some water. Now here this bank refers to the river bank. But while if I say the second sentence, like I went to the bank to draw some money, now here this bank refer to the bank where we keep our money. Okay, so there's this phrase that word is known by the company it keeps. So we cannot keep our embeddings of the words as static. That was used to happen with the traditional or statistical uh, word embedding representation that was done using the word to vec or globe embeddings that unfortunately we have not covered in our course, but some extent of it, like one hot encoding or ordinal encoder you can think of that. In that case, what if we do, uh, if we have the same word, then the embedding will be remain same for it. No matter in which context it appears, the embedding for the word will remain same throughout the training process. It won't change. Okay, but in general, we see that the meaning of a word can change depends upon how it's used in that sentence. Okay, so we want the contextual aware representation and the contextual embeddings. Okay, yeah, so that's the part that I said that the word to wake in the globe models, that was the traditional way of doing this embedding for the word. Okay, they use the static embedding. That means you will only get the same embedding for the word. You are not going to get a dynamic embedding based on the context that you are have. Okay, another part or motivation for moving to the transformer was okay, I think it's not fully visible, was the sequential bottleneck that we had for our RNN encoder decoder architecture. Okay, even though we have seen one Bandhano attention idea that was covered in the implementation part of week 9. Okay, which in which case also we used the encoder decoder architecture with Bandhano attention, but there also we had this bottleneck that RNN will process everything sequentially. Even though we already have our entire sentence in hand, like whatever sentence you have, like I want to go home, even though you already have this sentence, you still need to do the sequential task in which RNN will process each block one by one, passing its output to the next block, and that will pass it output to the decoder, and the decoder will also move things sequentially. Okay, so no, these are not from the DL. Okay, yeah. So this idea that everything will work sequentially, we have to wait for the next output to come, only then we can proceed further. Okay, so this was a bottleneck in terms of training time. Okay, so we want to do everything here parallelly. Okay, so that's where the transformer comes. Okay, what it does, it will make everything parallel. Okay, your entire encoder architecture, okay, everything will work parallelly. Same for your decoder, everything will work parallelly. Okay, and the output of the encoder will feed into the decoder after it gets completed its training. Okay, so that part will remain same as it is. Otherwise, the other part, that the sequential part will be removed now, and everything will start working parallelly. Okay, how we do that, that we will be seeing in each of these blocks one by one. Okay, so starting with one, yeah. Okay, so starting with the encoder part of the attention of the transformer architecture. first we have to define some notations. How we define our data metric X. It is of shape n cross t. N here refers to the number of tokens or the sequence length that you do after trimming and padding. So after all the essential pre-processing steps that you do, okay, whatever the sequence length or the number of tokens that you remain, that's your n. Okay, d is your dimension of your token. Okay, and that will be stacked row wise. So n cross t. Okay, so you have n sequence length, and each of your token is of d dimension. Okay, that's your matrix X. You will feed that matrix to encoder. Okay, so X is also n cross t, and encoder is also of n cross t. Okay, so encoder is also of n cross t dimension. Okay, now how the things will work here is in each of our encoder block. Okay, there will be some d transformer block. Okay, so we will be stacking these transformer blocks on top of one another. Okay, and there are d such blocks. In the original paper of attention is all you need, they stacked I think around 6 transformer blocks. Okay, but this how many transformer block you need, this is a hyperparameter that we choose by ourselves. Okay, so we feed a n cross d matrix. Okay, and the output will also be a n cross d matrix. Okay, so till now any doubt here?
Sir, is it encoder?
Sorry, can you repeat, Priyanshu? Is this no, this is the encoder block. Okay. Currently, we won't be going into the encoder only or decoder only or encoder decoder. We will be seeing everything together. Okay. So that's the initial part that they did in the attention is all you need paper. Okay. So that's the architecture that we will be seeing today. Okay. No problem. Okay. Yeah. Okay. So let's now zoom into the transformer blocks that we have. Okay. Now in the transformer block, again, look that the input that will be feeding to one transformer block will be of shape n cross t. Output of the transformer block will also be n cross t. Okay. Now, what we will be doing for each of our metric X that will be passing to the transformer block, there will be two ways that we will be moving this matrix. Okay. One, it's going to straight, and one, we will pass it to another block called as multi-head self-attention. Okay, and the output of multi-head self-attention is also n cross t. Okay, so the input of multi-head attention is n cross t, output is also n cross t, and that will be passed here. Now what does this called, this thing that we are doing here, what does this does?
Element wise addition.
Yeah, that's okay, but like we are passing this two ways, so this thing we did before also, so what does this call?
Skip connection, residual.
Yeah, yes, correct. Okay, this is the skip connection part. Okay, in the ResNet architecture for the CNN, we saw that. Okay, so the same thing we'll be doing here also. In each of our transformer block, we do this skip connection part for smooth flow of gradients. Because transformer architecture becomes very complex, so to stabilize the training, we will be using two types of tricks here. One is the ResNet connection trick that we have applied in the CNN architecture. Another is the layer norm that we will be I will be soon showing it how we do that. Okay, so these two things are done to stabilize the training. Okay, so one we directly pass X, and one we pass X to the multi-head self-attention. Okay, both you are just going to add it. Now output of that is passed to the layer norm. Okay, this is the normalized or another trick to stabilize our training part. So we will be looking at layer norm into a little bit more detail a little while later. Okay, but let's look at what happens after layer norm. After layer norm, again you are going to apply the skip connection part, but now one part will be feed to the feed forward neural network, in which again, if you look at the output, the input to the feed forward is also enclosed T, output is also enclosed T, and that is passed to with this skip connection. And then again, you are going to apply layer norm, and that after that, whatever output you are going to get will be passed. Okay, and the final output will be n cross T. Let me repeat it again. So things might get a little bit complex here. So we started off with this encoder, in which we have D transformer block. Okay, in each of our transformer block, okay, the input will be n cross T, output will also be n cross T. So that's why the final output of this encoder, because each of transformer block will output n cross T. So when you do this computation, the final output of this encoder will also be n cross T. Okay, in each of my this transformer block, we take this n cross T x matrix and we pass it in two ways using the skip connection. One way was using the multi-head self-attention. We will look into it what actually happens in the multi-head self-attention, but for now think of it like some box in which we are passing it and it will output it as a same dimension matrix. And using skip connection, we are going to add them, then pass it to the layer norm. This is kind of a normalization technique. We will look into it a little while later. And then output of this layer norm will be feed to feed forward, and using skip connection, we are again going to pass it same as it is. Okay, and that's how we will again pass it to the layer norm, and finally we will get the output of one transformer block, which is of the same dimension n cross t. Okay, so input for multi-head is n cross t, output for multi-head is also n cross t. Input to the feed forward was also n cross t, output for the feed forward was also n cross t, output of the transformer was also n cross t. So till now, dimension has not changed at all. Whatever goes into the input, the same dimension remained at the output also. Okay. Now this was done in the original paper. Okay, that they keep the dimension same. It's not necessary for us to do it same, but that was how it was configured. Okay, if you want, you can change it also. Okay, so far any doubt? Okay. This will again not appear actually. So now we will look into the multi-head self-attention block. Okay, so here the input is again n cross t, as I said here in the previous part, and the output is also n cross t. Okay, now how it's done is you will have the uh, data matrix that will be passed to different self-attention block. Okay, now why we use multiple attention blocks here? Okay, the analogy for using this is kind of similar to what we do for CNN. Okay, we use multiple kernels so that they get different type of feature representation. Okay, the same analogy we use it here, that we use multiple attention head so that each of them will learn different kind of representation. One can learn about the verb, one can learn about the subjects, one can learn about other semantic meanings. Okay, so each of these attention head, we think that they will learn different kind of representation. The same analogy that we use for using multiple kernels for our CNN architecture. Okay, so our n cross t matrix will be feed to these different attention head. Okay, suppose we have h attention head. Okay, so what they did in the original paper is, if suppose your dimension is 256 for your embedding dimension, that is your d is 256. Okay, and you are using 8 attention head. Okay, so you have 8 head here. Okay, so the dimension or the output dimension for each of these attention head would be 256 by 8. Okay, so I think that comes out 64 or 32. I think 32. Okay, so that will be the output dimension for each of these attention head. Okay, so that was the dimension that it is mentioned here using dv. Okay, so that just divided it by the number of head. Okay, and that was the dimension that they kept for this TV. In the end, they just concatenate all of that output. Okay, so it's like n cross TV, and then again you will be having one more DVs here. Okay, for each of these attention heads. So in the end, you will be getting n cross D matrix again. Okay, so yeah. Okay, after concatenation, you again pass it to one linear layer for more projection, and then get the n cross D dimension matrix again. Okay, so let me repeat it again. For the multi-head attention, you have your input matrix as n cross D. You will be passing it to multiple self-attention blocks. Okay, now there can be h such block. Again, this is a hyperparameter. In the paper, I think they decided it to be 8 heads here. Okay, no need to remember how many heads were there in the original paper. Okay, so each of these head, okay, will have the same dimension output. So what they did there is they just kept the dimension output dimension each of these head was the d by h. Okay, so as I gave the example, if my d here is 256 and I choose 8 attention head, then the output dimension of each of these head would be 256 by 8. That I think comes around 32. So this would be like n cross 32, n cross 32, n cross 32. I will concatenate them. Okay, so it will become again n cross 32. Then 32 will come and till 8 times, so it will again become n cross 256. Okay, that was n into h times dv. Okay, so they purposefully kept the dimension of h times dv to be same as d, although we can choose it to be different also. Okay, but in the paper they kept the dimension of h times dv to be same as d. Okay, after concatenation we pass it to a linear layer that just again weight matrix multiplication. Okay, to get the dimension of n cross d. Okay, so any doubts so far? Okay. Okay. So revisiting our self-attention motivation that we had. So suppose the sentence is I want to go home. Okay, and my query word is go. Okay, then I will look into each of the words that I have in my sentence. I want to go home. Okay, that will be my key. Okay, and what I'm going to compute now is that for let's suppose if I want to do the embedding for my I word. Okay, then how much importance this I should give to go. Okay, what is its context with go. Okay, so that is done using this score formula that we have already seen, that it will be the softmax of this part, that is the embedding of go times embedding of I. We take the dot product and we do the softmax on top of that. Okay, to normalize this score. Okay, now one thing that I wanted here, that we keep the query part constant and varying over the key part here. Okay, so query part will remain as a constant and the variation will happen over the key part. Okay, so for the query key pair matrix, if we have, okay, the qk and v matrix, okay, the qk transpose that you are going to do, we are going to get this 5 cross 5 matrix. Okay, and when you apply softmax on top of this, the softmax is done over row wise. Okay, because this will be my query for my first word. Okay, so query part will remain constant, so e power I in times I divided by n, varying over this part. Okay, over row wise. So when you apply softmax here, it will be done row wise. So softmax on this row, okay, and softmax on this part, and so on. Okay, So far, any doubt?
This is the same attention, I mean, self attention we discussed in the week 9.
9, yeah, yeah,
Yeah.
correct. Self attention, same thing. Okay, that you will be having these WQ, WK, WV matrix. Okay, you will multiply it with your X matrix. You are going to get your Q, K, and V matrix. Okay, so the dimension here, if I talk about, we keep the dimension of Q and K to be same, and this has to be same. Only then you can do the dot product. Okay, so the output dimension of Q and K here would be same. Okay, V you can choose it to different. Okay, but most of the time we choose it to be the same as DK only. Okay, so you do this dot product here, so you're going to get QK transpose. Okay, then you are going to pass it to the softmax after doing the scaling. Okay, for the variance in permutation, and then you are going to multiply it with uh, your V matrix here. Okay, and that's the final output of attention block you are going to get. Yeah, any doubt here?
Sir,
Yeah.
here why we are adding means what's the need of adding WQ, WK and WV?
uh, these are to get different kind of representation for context that we have. Okay, so we want the different contextual aware representation for our embedding, and we want it to be dynamic with respect to the word that are appearing with that sentence. Okay, so Q and K, the query and key matrix here, helps us get that attention score here. Okay, and V is the value part that will helps us get the embedding of that finally multiplied by the attention score.
Means before we also we see that it is also calculating same only.
Before, I mean, where?
Before means in few slides up you was doing dot product of
uh,
this one, yes.
yeah, so this Q that you are seeing here,
Hmm.
okay, that Q is obtained by the product of WQ and X. Okay, so it is also learned, it's not fixed. Okay, we want to learn this query embedding here, we do not want it to be fixed. Okay, so that's why we use this one more parameter WQ. Okay, multiplied with X, we are going to get this uh, Q matrix. Similarly, you are going to get this K matrix and V matrix, and then do the final things that you have. QK transpose softmax over that multiplied by V.
Okay,
Okay,
understand.
yeah, great. So now let's talk about the dimension more little bit. Okay, so you have your n cross d matrix X here. Okay, you are going to multiply it with WQ, WK, and WV. Okay, so what should be the size of WQ? It should be of size d cross something, right? Only then this multiplication is feasible. WK also should be of size d cross something. Same goes for WV. Okay, so the size of Q and K has to be same. By size here, I mean the output size. Okay, that is the number of columns here. For Q and K has to be same, because in the end we want to do the dot product between them. So that can only possible when the size is same for their output vector. Okay, so both Q and K will have the output dimension of dk. That's the notation that they keep. Okay, so WQ will be of size d cross dk. Same WK will be of size d cross dk. That's why the output of XWQ will be n cross d times d cross dk. So the output will be n cross dk. Okay, same, X is my n cross d, WK is d cross dk. Okay, so the product will be n cross dk matrix. When you do this computation of QK transpose, Q is n cross dk, K transpose will become dk cross n. So the output will be n cross n matrix. Okay. Then you do this scaling for the variance part. Okay, and to stabilize the training. Then you apply softmax here. It has to be done row wise. Okay. Then part comes from the V part. Okay. So you have this WV. Okay, which will be of size d cross dv. Okay, now in the original paper they kept the size of dv as same as dk, but if you want you can choose it differently also. Okay, so size of wv would be d cross dv. The product of x and dv wv will become n cross d times uh, d cross dv. So final output will be n cross dv. Now what will be the output of this part then? What will be the dimension of that?
N cross dv.
Yeah, correct, n cross dv. Okay, that's the dimension of this self attention equation. Okay, now that's what happening in each of these self attention blocks. You are going to stack, oh sorry, not stack, you are going to use multiple such blocks. Okay, and because we have the entire sentence already in hand, okay, each of these self attention output can be passed or can be trained parallelly. Okay, there's no dependency upon each of these different attention self attention blocks that you are using. Okay, so each of those 8 attention, so let me go back here, the transformer block. Okay, so each of these different attention blocks that we are using, okay, they can be the input to that can be passed parallelly. Okay, now final output of each of these block would be n cross dv. This we concatenate them, pass it to a linear layer. Okay, and output of that would be your output of one multi-head self attention. Okay, you do this process multiple times, that is you stack them multiple such things. Okay, and then pass it to the feed forward network, and after that you will be having repetition of these transformer blocks here. Okay, so that's the architecture of encoder part. If I repeat it again, one encoder block will have multiple transformer block. Okay, d such transformer block, let's say in each of the d transformer block there would be one multi-head attention and one feed forward neural network part. Okay, in one multi-head attention there can be multiple self attention blocks. Okay, so one encoder will contain the self attention, multiple self attention, that is called as the multi self attention part, one feed forward part. Okay, that will be in fact one transformer blocks, and this process you can repeat multiple times, so that's why you have d transformer blocks. Okay, so training inside the multiple self attention part will be done parallelly, but this training, okay, that is the output that is going from one transformer block to another, this part of course has to be done sequential. Okay, because the next transformer block can only process when it gets output from the previous transformer block. Okay, but inside our multiple self attention blocks, okay, we can do the parallel work here. Okay, because these attention block does not depend on each other. Okay, it's just that yeah, their output has to be concatenated and then feed it to the next feed forward neural network part. Okay, that is one thing. Yeah, so the final part, that is the feed forward neural network that we can see now. Okay, before that, any doubts so far? Okay, yeah, so now the layer gnome, uh, first of all it does not change the size, so whatever type of size you are going to feed it to this input, okay, the same size you are going to get as an output. Okay, so okay, this it's written as tv but it should not be. Okay, Yeah. So what it does is it's similar to what the same kind of equation we have seen in batch normalization. Remember, okay? There also what we do, we first separate the mean divided by the standard deviation, okay, and then we call that as a x hat. That x hat is going to multiply by with some gamma, and we add the beta to it, okay. And these are the learning parameters, the beta and the gamma. These are also learned during the training, okay. The only difference between the batch normalization and the layer normalization is, in the batch normalization, the mean and the variance that you were calculating were across the batch, okay. While in the layer norm, if you see, the mean calculation is happening across the feature dimension. So you are summing here across the D. Here also you are summing up across the D, okay. So in the layer norm, it is happening across the feature dimension. In the batch norm, you are doing it across the batch, okay. So that's the only difference between layer norm and the batch norm. Otherwise, the entire idea is same as batch norm.
So can we say then batch number is temporal, the other one is spatial?
Yeah, kind of you can say that, okay. Yeah. Any more doubts? Okay. So the last piece of the encoder is the feed forward neural network. It's the same kind of structure that we see. It's just that so far we have not introduced any kind of non-linearity. Okay. If you've seen whatever things that we were doing, the passing our x to the multiple self-attention blocks. Okay, so we are projecting our query, key, and value matrix. Then output of these are done using the softmax was one, okay, but that was just to normalize the score, okay. And then in the end we concatenate the output of the multiple attention blocks. Then again we pass it to a linear projection only, okay. So far we have not done any kind of non-linearity. The non-linearity will come in the feed forward neural network part, okay, in which what we do, the output of the multiple self attention block, okay, after doing the ResNet connection and the layer norm, okay, the output you are going to get from that part will be n cross d, and that will be feed to your feed forward neural network, okay. That will also output as a n cross d, okay. So the structure is same, we just keep one hidden layer, okay. So we pass our n cross d input matrix to this linear layer, okay, and then pass it to the ReLU layer, then again pass it to the output layer, okay. So there would be just one hidden layer here, okay. So there would be just two matrix. One would be of size d times dff. Dff is the number of neurons in the hidden layer, and then another matrix to again project it to the same dimension, dff times d. If you add the bias, then in the first one it's dff, in the second one it would be d, okay. So in the feed forward neural network, we only keep one hidden layer, okay, and I think usually they keep it to the double the size of uh, the input dimension. So double, or I think the 4 times the size of input dimension. That was the size that they choose for the hidden layer in the original paper. So if they first D, then they choose the hidden layer size to be either 2D or 4D. Okay. So that's about the feed forward neural network. Any doubt here? Okay. So let me again summarize it once more. Yeah, I will now just use this part to summarize. Okay. So we have our input metric x, which is of n cross d dimension. Okay. We pass it to multi-head self-attention block. What will happen in the multi-head self-attention block? There would be multiple self-attention block. Okay. What does each of these self-attention blocks do? It's going to compute our attention score and value embeddings. So there the computation of qk transpose softmax over that times v will happen. Okay. Each of my self-attention block will output in n cross dv. Okay. Later you concatenate all of the output of the self attention block. Okay, so if you have h head, okay, the output after concatenation would be n cross h times dv. Okay, as dv was the output dimension that I chose for the self attention, then the output you are going to get after concatenation would be n cross h times dv. Okay, that is again passed through one linear layer. Okay, and that will be give you as a output dimension of n cross d, and that's the output dimension for my multi-head self attention. Okay, that's added with the resonate connection thing, passed it to the layer norm. Again, it's not going to change the dimension, so n cross d is going to go as a input dimension, n cross d is going to get you as a output dimension also for layer norm. This will be passed to one feed forward neural network, in which there would be only one hidden layer that's generally keep the either twice or four times the size of dimension. So if it is d, then it can be like 2 times d or 4 times d. Okay, so it's like we are going to pass this n cross d to one hidden layer that would be like 4 times the size of input dimension. Then again we project it to the same dimension only. Okay, so that's why the output of the feed forward is also n cross d. Again, this is done using the resonate connection so that the gradients will flow smoothly. Pass it to the layer norm to stabilize the training. Okay, and after that you are going to output your n cross d. This was for one transformer block. This thing you can do it multiple times or stack multiple such transformer block one top of another. That was what we do or we did here. Okay, and after going through that, the final output that you are going to get would be again n cross d. That will be your output of encoder. Okay, so any doubt in the encoder part?
Sir, can you please explain layer norm?
Okay, sure. So once you have understood the encoder, the decoder part will not be that much hard. Yeah. So in the layer norm, what we are doing, first of all, one thing to notice here that the dimension will not change. dv is wrong written here. Okay. So whatever you passed as an input, the same output you are going to get. Okay. How we do the layer norm? For our input x, what we do is we find the mean and the standard deviation of it. How we find the mean? If let's suppose your input is 1, 2, 3, 4. Okay. Let me choose different. Okay. Now suppose your input is 1, 2, 3. Okay, so this is your n cross d matrix. Okay, so n here is 2. Okay, so you this means you have two words you can think of. Okay, d here is 3. So each of your word dimension is 3. Okay, so your x1 is kind of 1, 2, and 3, and then you have your x2, which is 3, 4, and 5. Okay, so you have these two words, and this is the embedding of these two words. Now, if you are going to do the layer normalization, then what you are going to do, you first have to find the mean. Okay, so here you are going to find the mean across the feature. Okay, so the mean for x1, okay, would be what? It's 1 plus 2 plus 3 divided by 3. So 6 by 3, that is 2. Okay, mean for x2 would be 3 plus 4 plus 5 divided by 3. So 5, 4, 9, 3, 12 by 3, 4. Okay, now similarly you have to find the standard deviation also. Okay, that I'm not going to calculate, it's a little bit more complex. Okay, but similarly you are going to find the standard deviation also for this. Okay, and same for this. Then what you are going to do is you are going to calculate the x hat. So x hat of 1 is x1 minus the mu associated with it Okay, that is the this mu. Okay, that will be 2 for this, and the standard deviation whatever you get. Okay, sigma 1. Okay, similarly you are going to do for x2 also. Okay, now once you get this
That
x,
answers. Thank you.
okay, oops.
But sir, how it was determined that for somewhere it has to be taken as a layer norm and at other places it should be batch norm?
See, these are all the empirical things. So they tried with different experiments. Okay, it worked somehow. Okay, for most of the things, we do not have any much mathematical proof like why it happens. So these are just the empirical proof that we have that these things work. It works. Okay, like one thing that we have for like atom, that there's this problem with the atom that it failed to converge most of the times, but still it outperforms most of the time, so that's why we use it. Okay, so these things are like mostly empirical.
So basically, it will standardize means essentially you're taking a vector and projecting it to the unit sphere. So that way, your learning is not unbalanced. Rather, it's a learning. It's giving equal weightage to all the features. That is what I think we were taught in earlier weeks, right? So it doesn't become like a ellipsoid or whatever. We kind of try to make it a sphere.
Yeah, yeah, see, the main goal for this was to again to stabilize the training and to make it things work, because otherwise the training will become more complex if you do not use the layer norm part and the skip connection part. So okay, so this was the end goal for them to use. Now layer norm here work better rather than the batch norm. Okay, so yeah, anything else, any doubt in the encoder part? Okay, and let's just quickly do one check of number of parameters. Okay, so the main parameters that we had was our wk, wq, and wv matrix. Okay, and we keep the size of them as d cross dk, d cross dk for q and k. For v, we keep the size of d cross dv. Okay, now to simplify things, if we assume that dk is same as dv, that means the dimension of these three matrices is same. Okay, then what you are going to have, you are going to have 3 times d cross dk parameter. Okay, now you will be having h such head. Okay, so you will be having h such different h such matrices. Okay, so what in the end equation will become 3 times d cross dk times h. Okay, now assuming things more simpler, as I told in the initial example, that in the initial paper what they initially decided for the each of my self attention block, its output dimension would be nothing but d by h. That is if the my dimension for embedding dimension is 256 and I am using 8 heads, then each of the output dimension for each of my head would be 32. So that after you do the concatenation, the output dimension also becomes the 256. Okay, so that's what written here, that hdv is d. Okay, so again, if coming back to the parameter calculation, we have 3 such matrices. First assumption was that if dk is equal to dv, okay, then it will be like 3 times dk, 3 times d times dk such matrices, and you have h such head, so h such matrices, so 3 into d into dk into h. Okay, using the second assumption, that is hdv is equal to d, the parameter calculation becomes 3 into d into d. So that's what written here as 3d square. Okay, then what you are going to do, you are going to do that linear projection. Remember, after doing the concatenation, you do the linear projection also. Okay, so that takes the input dimension of hdv and output in d dimension. So because of our assumption that hdv is equal to d, this will be 1d square. Then comes the ANN part, or the feed forward neural network part. Okay, so there will be two metrics. Yes.
sir, I had a question on this one. So basically, if I look at the self attention, there
Hmm.
are n number of words. So each word has to look at its its n cross n. But embeddings are d dimension. So the way you are
Hmm.
doing is, let's say in the original paper, the embedding dimension was, let's say, 256.
Yeah.
You're kind of deciding eight parallel heads. So 256 by
Hmm.
8 happens to be
Yes.
32. So
Yeah.
you're kind of splitting 256 into eight parts, and
Yes.
each part is focusing on a subset of the original matrix. Because let's say whatever it is, and then after these eight parallel heads, which are independent of each other, do the computation, then you're concatenating it, so that you
Yeah.
get your 256 back. Then after
Yeah.
that, you do the FFN and all that. So essentially, if my dimension is d, I can take k, but it has to be some integer multiple, right? Or usually people will choose like
Yes. Yeah.
either 4 or 8 or 16, because these are all binary. It's just easy, right? Because
Yeah.
from a
Correct.
conceptual standpoint, I think that is what we are doing, and this is probably the breakthrough, because the heads are parallel. Hence the complexity from I think d cube become d square, right? So it was able
Yes.
to crack through. I think that was the crux of the. So you are discussing the same thing here, right? Except that concept still remains the same, except how we do it and all that is a little different. That's all.
Yeah. So
Yeah.
they do it purposefully, keep it as same. Okay. Even though if you want, you can keep it as different also. But yeah, whatever you said was correct. That initially they kept everything here as same as that. You are going to divide each of your heads into such that, or choose the number of heads in such a way that after the concatenation, you get the same output dimension as your input dimension. Okay. Yeah, but
Thank
it
you very much.
won't be just one thing here, that it won't be exactly like 1 minute. Let me choose the pen. It won't be exactly like this, that you have, let's suppose this is your 256 dimension, then it won't be exactly like the slicing, because what you are doing is the matrix projection to do this. Okay, so it won't be exactly slicing, but through this linear projection, or through this learned projection, we are doing this. Uh, okay, so it won't exactly like slicing, but for simplicity you can think of it like that also. Okay.
So you're projecting it. It's almost like what we learned in encoder. Like you want to reduce the dimension,
Yeah.
and then after that in the decoder you will kind of project it upwards. Here it is like the encoder. It will be downward projection. You're going to lower dimension.
Yes.
Once you learn your criticality, then after that, once you are in decoder, you start projecting to the upper dimension. So in some sense, from 256 will go down, and after that, in the decoder layer will again come up.
Yeah.
That's basically what
Correct.
was the architecture. Yeah.
Yes. Okay. So from your 256 dimension, you are going into the lower dimension. Okay. You are learning some representation. After that, you are concatenating all of them to get the same dimension. And again, one more layer of linear projection you are going to do before passing it to the feed forward neural network. Okay. Once this is done, then you pass it to the feed forward neural network. Okay. And yeah. So yeah, one more assumption, that here it is written that the hidden layer size is 4 times d. Okay, so if you choose that, then it is d times 4d and 4d times d here. Okay, so 8d square is coming from here. So approximately 12d square parameter will be there, excluding bias. Okay, bias is generally added here only. So if you want to add bias, then dff plus d will also come here. Okay.
So it should be plus 80, right? Because for every node you'll have one bias. So it should be, if you have got D nodes and D biases, there are, that's how it should be, right?
Yeah, so there would be dff plus d bias. So if dff is 4d, then 5d bias would be there.
Yes.
Okay, 12d square parameters and 5d bias. So is the parameter calculation clear? How we calculate it?
Sir, is this a standard formula? I mean, is this a standard computation
This
for this?
is, yeah, this is a standard computation, assuming uh, these things holds. Okay, that your dk is equal to dv, that the output of query and key is same as the output of your value. Okay, and you are essentially dividing in like equal dimension for each of your heads. So it's like your head output dimension is just nothing but d by h. Okay, and your hidden layer size is 4 times the input dimension size. Okay, assuming in that case only this is correct. Okay, otherwise you have to again go through that So see how you start calculating the parameter for transformer is you start with this WK-V pair first of all. Okay, first decide what is their size. Okay, let's suppose forgot this formula first of all. Okay, so first decide what is the size of these each of your WK, WQ and WV. Okay, for WK and WQ it's going to be same. Only thing that can change come up here is WV. Okay, so these three will have the same size across all heads. Okay, so their sizes is not going to change across the heads. Okay, so you will be having d times dk plus d times dk plus d times dv parameter multiplied by the number of heads, because these many heads you are going to have. So these many uh, again the same size of matrix you are going to have. Okay, that's why it's multiplied by h is written here. After that, what you do, you pass it to a linear layer. Okay, but what is the input that goes to the linear layer? It's the h times dv, because you concatenate the output of the self attention blocks. Okay, so that's why h times dv, and the output dimension of the linear layer is the same as the input dimension, so it dimension will remain h times dv into d. Then comes the feed forward neural network that's going to have these two matrices, d times dff and dff times d. So I don't think so there should be any problem in this part. Okay, if you just remember this architecture here. Okay, now this was the parameter calculation for one transformer block, because these things are happening in one transformer block, right? In one transformer block you are going to have multiple head attention. Okay, passing it to the linear layer, then passing it to the feed forward neural network. Okay, if you stack some d transformer blocks, or let's suppose some, I should use some other notation, let's suppose some uh, b transformer blocks, then you are going to multiply this entire thing by that many number also, because the same number of parameters will be there in each of these transformer block. Okay, so are the things clear, or do you want me to repeat it one more time? Okay, good. Now we are going to look at the decoder part. Okay, most of the things for this would be same, only one place that's going to change in the self attention part, in which we will be doing the masking. And one more thing that we are going to introduce here is the cross attention part. Otherwise, more or less, it's kind of same. Okay, the same thing that we are going to have multiple transformer blocks. Okay, in which for the simplicity we are keeping the dimension to be the same as n cross d here. Okay, that it takes n cross d as an input, and the final output will be n cross d also, and your output of encoder. Okay, and the output is n cross d again. It's going to have these multiple stacking of transformer blocks. Again, each of these transformer blocks will have the same kind of structure. Okay, but what we call it as now is a masked multi-head self-attention instead of the vanilla multi-head self-attention. Okay, otherwise more or less it's same n cross d will be passed with the same skip connection will be there, layer norm will be there. Then one more block will be added here, that is multi-head cross attention. Okay, this is the part where it gets input from the encoder block. Okay, and then it's again going to pass through this skip connection, layer norm, then feed forward neural network, then again layer norm. Okay, and that will be the output of your one transformer block. So two things that were changed here was that instead of the simple multi-head self-attention, we had this masked multi-head self-attention. This was to prevent leakage from future tokens, and we had multi-head cross attention to get the context from our encoder block. Okay, so how does this masked multi-head self-attention equation looks? Okay, the initial part is same, that you are going to have QKV matrix. Okay, so you are going to multiply your y, that was your input for your masked multi-head self-attention. Dimension is n cross d. Okay, so you are going to get this QK projection, then QK transpose, so n cross dk, n cross dk. The output of this you are going to get is n cross n. Okay. So yeah. Okay. So you are going to divide it by square root of dk. You are going to apply, yeah, before applying the softmax, you are going to add this masked matrix. Okay, which will be kind of like a upper triangular matrix that we'll be seeing in soon how it will look. But you are going to add this matrix just before you are going to apply the softmax. Okay, after doing the scaling of this dot product, after that and before applying the softmax, you are going to add this masked matrix M. After that, the rest of the part is same, that you are going to apply softmax and multiply it with V. Okay, so only change that is coming here in the from encoder to decoder part is addition of this matrix M. This matrix M size, can anybody tell me what will be the size of matrix M?
D cross D.
Okay,
N cross N.
N cross N is correct, because your QK transpose is also of size N cross N, right? So two matrices can only be added when they are of same size. So M also has to be of size N cross N. Okay. Now let's look at how this mask matrix look. Okay. Suppose my sentence, so target sentence is, I am going home tomorrow. What we do in the teacher forcing is we pass our actual label also. Okay. Unlike the auto-regressive way, in which what we do is we do the prediction from the first part, and that part will be fed. Instead of doing this part, we do the teacher forcing way, that is we use all the labels that we already have, that is the original entire sentence. Okay, and we mask it. We mask it using this numerical trick that we have. Starting this, we do this starting token. Okay, that will be feed. Okay, and the position here, that because we can see the starting token in the first timestamp, we keep it 0, but we cannot see the later token that we have, I am going home tomorrow. Okay, so we keep the values for that place to be negative infinity, negative infinity, negative infinity. Okay, now what numerical will happen, that they will be masked. How they will be masked is because of how this computation works, that what we are doing is we are adding M to this QK transpose output. Okay, if the value there is 0, then the value will remain as it is, nothing will going to change at that place in this QK transpose output. But if the value there is negative infinity, okay, then the value of QK transpose plus the negative infinity is going to give you negative infinity. When you apply the softmax normalization on that negative infinity value, then what value you are going to get? It's e power negative infinity divided by the summation score, right? Okay, so because of e power negative infinity, what will be the value of e power negative infinity?
0.
0.
Yeah, 0, correct. Okay, so that part will become 0. Okay, so the output of softmax at that position will become 0. That it essentially is going to say that there's no attention score, or there's no need to put attention on that part. Okay, because that's what this part was doing. Good evening, right? Everyone. This was assigning the attention score, and we will keep it as 0. Okay, so the first okay so that was the numerical trick, that it's going to mask the future token when we keep it as negative infinity. In the second iteration, we can see as, and because in the second part the word would be I, so we can keep 0 here also, but we cannot see the later tokens because we want to predict the M and the future tokens also. So that's why we will keep the rest of the token as negative infinity. So the rest of the things will be masked out. Okay, and following that, this is how the entire M matrix will look like. It's kind of a upper triangular matrix. Okay, in which all entries below the diagonal will be 0. Above the diagonal, it will be negative infinity. Okay. In terms of more masked representation, this is how it will happen. First, only starting token will be visible. Everything will be masked. Then I am going home. I am going home tomorrow. Okay. 1 minute. Give me 1 minute, guys. Yeah. So sorry for that. Let's resume it. Okay. So is the mask thing clear? How the masking happen for to prevent the future tokens?
So basically, by putting minus infinity, when we take the softmax,
Hmm.
it will be a very large negative number. Hence, your probability will be zero. So that's the trick
Yeah.
to kind of that you will not be able to see any future tokens,
Token.
only
Yeah.
whatever has happened prior to you.
Yes. Because it's going to give the attention score for that to be 0, and when you are going to multiply it with the value embedding, it's going to give you output as 0 only. So there's no attention that you are going to put it there. So you are going to prevent it from seeing the future tokens. Okay. So
Sir,
that's
is this happening all during training phase?
sorry.
Is this happening all during training phase? Or
Yes, this only happens during training phase. Okay. During testing phase, what happens is we do the auto regressive manner. That is the prediction of first token. That is, let's suppose the first token is passed. It's going to predict I. This I will be used, okay, to predict the next token during the inference time. Okay. So during training, we already have the original label, but we do not also want our model to see them, so we do this mask trick. Okay. Yeah. So, any more doubts here? So, other change that was there between encoder and decoder was the cross attention layer. Okay. This is also the same thing we are doing here. Okay. Again, the same QKV pair we are going to make, but notice here the Q matrix or the query word is coming from Y. Y was the input to the decoder, while the K and V, key and value pair, are coming from the X part. That is my encoder. Okay, so that's the only change that you have to remember. That query comes from the decoder, while key and value comes from the encoder. Okay, as this is the sentence I want to query for. Okay, and that key and value will come from the encoder. Okay, everything else will remain same. That you are going to do the same computation here. QK transpose scaling by square root of dk. Here you do not have to do anything because it's already masked from the previous output, so there's no need to do the masking here. Okay, apply the softmax directly, multiply it with v. Okay, the dimension calculation for each of these matrix will remain same as before. Okay, the same n cross dk, n cross n cross n here, here n cross v. The final output will be n cross v dv. Okay, so only change here is query will come from the decoder, key and value will come from the encoder. Okay, clear? So yeah, that's all. Okay. So it's almost kind of the end of the transformer architecture. Now, one final thing that is remaining is the positional embedding. Okay. So if I have the sentence says I am going home, grammatically it is correct. Okay. But if I have the sentence of am going I home, grammatically it is not correct and it does not make any sense. But the transformer architecture that we have discussed so far, it's going to treat both of them as same. But we know that both of them are not same. Okay. Because so far we have not talked about the position uh, arguments that we have. In the RNN architecture, this was not an issue because there the things were working sequentially. So it was already taking care of the position because it was working like first I will go, then am will come, going will come, and home will come. So things are processing sequentially. So we already have the idea or the kind of version of our position. Okay, but in attention, because all of things we are processing parallelly, okay, we have lost our advantage of position. Okay, so why? So that's why we need now positional encoding. Okay. Now, in the modern LLMs, these positional encodings are also learned, just like we learned our word embedding. Okay. But in the original transformer paper, they did not do this learning process. Instead, they used one formula to directly calculate the positional embedding. Okay. And that was this formula. Okay. That was x position for to ith place is sine of position by 1000 power 2i by d. For the odd position, it is cos of position by 1000 2i plus d. Okay, so that's the value. Okay, so whichever the x position value you want to, okay, so x1 will come, so then 1 by that, okay, and 2 by that. So the x position vector will look something like this. Okay, now you do not need to remember this entire formula of how these things are calculated because these things you are not going to ask. Okay, and also these like a little bit heavy computation for calculating the positional embedding. Okay, but the main idea that you can remember is they calculated this positional embedding, and that positional embedding they added it to the original vector. Okay, original embedding vector. So the dimension of both of the positional embedding vector and the word embedding vector will be same. So that's why the output of these two will also be in the same dimension d. Okay, that's all they did. Okay, yeah. So any doubt here? One more thing that I have, yes, this part. Okay, that is some like kind of geometric intuition of this positional embedding. That if you look at this graph here, okay, as your dimension increases, okay, the position embedding, okay, will the changes between them will keep on reducing. Okay, you can look at the embedding values graph here. Okay, so as the dimension increases, okay, the embedding values changes will become less. Okay, why it was useful, it's like the denominator term that we had. Okay, it causes our sinusoidal wavelength to vary. Okay, so if you choose the dimension to be low, then because more words will have context to each other in the low dimension. Okay, so the encoding values will change because in that case if you are going to change the permutation, then it's going to affect a lot. Okay, but in the case of high dimensional case, or you have high dimension, then the context window will be very high. Okay, so there the frequencies or the wavelength frequencies will decrease. Okay, so the encoding values will not change uh, that much fast. Okay, yeah, so that's the end of the transformer architecture. Okay, I revisit it again. We have two blocks, encoder and the decoder. In the encoder block we have mainly two components. One is the multi-head self-attention, second is the feed-forward neural network. Okay, you combine each of these into one block and you stack multiple such blocks together called as the transformer blocks. Okay, in one multiple self-attention blocks, what happens? You will be having multiple self-attention blocks. Output of each of these self-attention blocks, you are going to do the concatenation, pass it to a linear layer, pass it to the feed-forward neural network. Okay, this computation happens as many times as many transformer blocks you have. Final output is your output of encoder. That output is going to feed to the decoder. In the decoder, there will be three parts: masked multi-head self-attention, cross-attention, and the feed-forward neural network. So again, more or less the idea is same, that you are going to have multiple transformer block. In each transformer block, you are going to have these three things: multiple masked multi-head self-attention, cross-attention, and feed-forward neural network. Masked multi-head self-attention. It's just that more or less everything will work same. It's just that before doing the softmax, we add our mask matrix. Okay. Otherwise, everything will be working as same as our encoder part. Encoder multi-head self-attention. Output of masked multi-head self-attention along with the layer norm and the resonate connection pass to the cross-attention, in which query comes from the decoder and key and value comes from the encoder. Okay, that's the only change that happens. Otherwise, the same attention calculation will work there. Output of this cross attention is feed to the feed forward neural network along with the same layer norm and the uh, resonate connection. Okay. After doing that, you pass that output to another transformer blocks and these things will work. Okay. Yeah, so that's the end of transformer architecture. And the positional encoding is to make into account of this permutation of words. Okay, you add this positional encoding. In the original paper, they used the formula for the standard saddle curve. Okay, but nowadays in the modern LLM architecture, you also learn this positional encoding. Okay, along with the word embeddings that you have. Okay, yeah. About the layer norm, it's more or less similar to the batch norm idea. That it's just that you find the mean and the variance across the feature dimension, then you normalize it, and you do the linear scaling thing. Okay, where these parameters gamma and beta are also learned. Yeah, that's the end of transformer architecture. Any doubt, anyone? Okay. Now, still the theory is not fully completed for week 10, although the main part was, or the heavy part for week 10 was the transformer architecture only. The later part is it's about how modern LLM thinks. Okay, it's about how the tokenization and things works. Okay, and the new paradigm shift that we are going forward is, instead of doing the full entire training from ourselves, we do the fine tuning on that. Okay, so that's the part we are going to discuss in the next session that Puneet is going to discuss. Okay, and as I already said, there will be no coding session this week. Okay, we'll be directly seeing the coding implementation next week now. So, any doubt, anyone? Yeah.
I have a doubt in week 10 graded assignment question 3.
Okay.
I don't want to discuss the answer, but then without giving x with only shift and scale given, shall we be able to calculate the what has been asked in the question? I'm not able to understand.
This one.
Yeah.
Okay, you are processing a single word embedding x of dimension 2 inside a layer norm block. Okay, the layer has learned the scale y, shift b, okay, and epsilon e. Okay, for simplicity, perform the standardization step x minus mu by u. What is the value of the first dimension immediately after the standard before applying? Okay, yeah, this should be given. Like for now, I don't think so. I can come up with any reasoning like we can do this. Yeah, yeah. Okay, this has to be given. This must be mistake. Let me report it to the instructor. Uh, Most likely they missed out uh, while configuring the assignment. Okay, so don't worry. What's the deadline for this assignment? Is 12/5. Okay, it's December only.
Another 4 days.
Yeah. Uh, Most likely it's the mistake, or if it is not, then I will convey it to the Puneet to convey to you to the next session. If it is not the mistake, else it's going to get updated by tomorrow, most likely. Okay.
Okay. It is not possible, no? That's what my
Yeah,
question
like
is.
for now,
Am I
I'm not able
missing
to.
anything? And I want to know. Am I missing
Uh,
any
like
concept?
like for now, I'm not able to think of any way to calculate this without knowing what the x is.
Okay.
Okay. So most likely there's no. Okay. Else I also have to think if it is there. Okay. Mm. Anyone else? Any else doubt? Let me
No,
just give me,
sir.
or just give me 1 minute. I have not made this question, so most likely this must be made by Puneet. So let me just confirm it once. Okay. Yeah, the x should be given here. Okay. Mm, okay. So I will inform it to the instructor. Most likely it should be fixed by tomorrow. Okay. So you can check it later. Okay.
Okay, thank you.
Okay. Any more doubt? Anyone?
No, sir.
Okay. Yeah. Great. So maybe I what I wanted here. Okay, so just this one question that we are going to do. Okay, what about the NPP? Yeah, sorry for that. NPP, first of all, we have not yet told about the dates for the NPP, so I'm still not sure whether we are going to have NPP this week or next week.
It is
I think sir said that 12th.
Sorry, one by one.
Sir Levin sir said that it's 12th.
It's
It's
12.
going
Okay,
to.
so that means next week. Yeah. Okay,
Yes, sir.
then next week. Okay, so from not, uh, we have not planned any session yet from our side. Okay. If you want in some session, if you left time, then we can cover some doubts that you have. Okay. Otherwise, I feel that I hope Livin sir has cleared all of your doubts regarding the track IO and the Hugging Face in your session, right?
Yes, sir.
That's good. So again, we will be using that for the tracking of parameters and loss curves. Okay. Otherwise, what you extra have to do is this time most likely you will be training the RNN for sequential learning model. Okay. And again, it's going to happen on Kaggle. Most likely, again, you have to make a report. So most of the things will be same. It's just that problem statement is just going to change. Okay. Yeah.
Pulkit,
Yes.
there is a
Karthik.
G form created for NPP1, right?
Yeah. For the
Anything?
discrepancy.
Yeah, I have some discrepancy. When this will be resolved, like you have some time frame for
So,
that, that it will be resolved by?
any deadline was given for that in the mail?
No, right?
Mm,
Nothing
uh,
like that.
the form it is still 30, but then when the results will be updated, we don't know.
okay. The deadline was 30. So we have not got the response yet. So if we get the response within this week, then the results will be updated by next week. Okay.
Okay.
Yeah. Okay. So by next week, at least I will give you the deadlines. This is
Okay.
only if we get the response in this week.
A response from whom?
From team side. Okay. If we get the team side response for the form, then we'll start evaluation again, and then the evaluation will take time. So by next week, that's why I was saying that it will get updated in your dashboard. Okay.
But the evaluation is not done by individual, right? It is done by some some software or something like that. Looks like.
Yeah. See, some part is done through manual check also.
Ah, is it
Okay.
okay?
And we do it in the group wise. So usually it's happen like two checks kind of things. So okay.
Because for me, I did the scratch, but I commented out the scratch model, so it gave zero.
Yeah.
Or
Don't. Don't worry. We will take care of that. Okay. In this, mostly the evaluation this time will be fully manual. Most
okay,
likely all of the discrepancies. But
okay, okay.
yes.
Thank you.
Yeah. Okay. So, any more query? Yes, Tisha.
No, sir, it's by mistake.
Okay. Yeah. So let's just quickly solve this question. So consider a single head scale dot product attention model inside the transformer encoder. The input sequence has three tokens and the embedding dimension is 4. That's where n is here 3, d is here is 4. So x matrix is 3 cross 4. So x1, x2, x3. Your first token is 1010. Second token is 0110. Third token is 1101. Okay, x1, x2, x3. The learned projection matrices WQ, WK, and WB are these as follows. Okay. Now, as WQ is of size 4 cross 4, the output of my head dimension would also be 4. Okay, we are using a single head here only. Now the scaling factor here is the square root of dk. Dk was the size of output size of WQ matrix, so that is square root of 4, so 2. So QKV matrix are defined as XWQ, XWK, XWV. All softmax operation are row based. Now first question asks us to compute the query vector for token 1. That is query 1. I want the query 1 vector. Okay, that's done using X1WQ. Okay, so it's if you want uh, the code wise, then it's just X times WQ you can do. Okay, so you can take this vector, multiply it with this matrix. Okay, whatever output you are going to get, that your query 1 vector. Okay, similarly you will be having query 2 vector, query 3 vector, that will together will form your query matrix. Same for key matrix, same for value matrix. Okay, now compute the row attention score between token 1 as query and token 3 as key. That is q1 times k3 and square root of dk. Okay, so just how we computed q1, similarly we can compute k1. Oh, sorry, k3 here. So we will be using this vector multiplying with this matrix. Okay, yeah, you are going to get k3. Okay, then it's just simple dot product between q1 and k3 divided by the scaling factor of dk. Okay, then the next question was the final attention output for token 1. Okay, that is the attention of 1 it is asking. Now if it is asking for 1, okay, then remember as I said that 1 will be kept as your query, so it will be fixed and you are varying over key. Okay, so what you need is here you need your k1, k2, k3. Okay, so I have already here calculated k1. Similarly you are going to calculate k2 and k3 just like we did here, or you can just simply multiply xwk. Once you get k1, k2, k3, you have to take the dot product of that with q1. So q1 times k1, q2 times k2, q3 times k3. Do the scaling using square root of dk. Okay, you are going to get this attention score a1, a2, a3. These are your attention score that you are going to get.
Sir, are these questions from PAs? I
This
mean, from week 10 PA practice assignment, or are these additional questions?
this might be in the practice assignment, or if it is not, then you can treat it as an additional. Okay, I think in the PA, the question is this one. This question is from PA. Okay, this one was not in the PA, so you can think of this as an additional question. Okay, if I just to show how the computation works for transformer. Okay.
Sir, can you please share this?
No, this notebook is used for internal purpose, so I cannot share the entire one. Okay, I can only share this question. If you want, you can take the screenshot of this question, or else you can check the recording also later. Okay. Yeah. So as we want the attention score for one token, first token, what we want our query has to be first. Okay, and key and value will vary. Okay, so this thing I did in the code wise manner. That was np dot x times wk. X was here my first token 1010. Okay, so x times wk, that's going to give me query vector 1. X times wq, that's going to give me key vector 1. Dividing by the scaling factor, I'm going to get row attention score 1. Similarly, x2 times wk, and here as you can see the query will remain same, only we will vary over key. So x2 and x3 will vary over key part. So that's how you're going to get your attention score 2 and attention score 3. This is my raw attention score. I want to normalize this using softmax. So that's what it is done here using the softmax formula np.exp. Okay, then I'm going to also calculate my value embedding. So v1, v2, v3. Okay, so how the attention formula works: alpha 1j times Vj. So alpha 1 1, alpha 1 2, alpha 1 3. Alpha 1 1 was this, but oh sorry, this alpha 1 1 was this, alpha 1 2 was this, alpha 1 3 was this. This has to be multiplied with v1, v2, v3. Okay, and you are going to do the summation of that. That's going to give you final your attention output. Okay, so is this calculation clear?
What are you explaining in the last part? This.
This part, see, what question was asking is final attention output. Okay, that is after doing this. So till now, was it clear?
Will be a matrix of 3 cross 4, no?
Which one?
The final attention of 1.
No, no, it won't be a matrix of 3 cross 1. So see,
It will be summed up.
yeah. So you are going to get these alpha 1 1, alpha 1 2, alpha 1 3. Okay, here I've named them as alpha 1 2 3. Okay, how they get it? We do the
This I
query vector.
understood.
This
Yeah.
I okay, good. Okay, after doing the softmax, this is what you are going to get.
Yeah.
Okay, now you are going to get value vector also v1, v2, v3 by multiplying your x1, x2, and x3 to the wv matrix. Okay,
Yes. Okay.
now what you are going to do here, alpha 1 1 times v1 plus alpha 1 2 times v2 plus alpha 1 3 times v3. So here it would be a1 times v1 plus a2 times, oh sorry, not this a, this one. Okay,
Okay.
after
Then
doing
finally it would be a vector of size 4.
yeah, vector of size 4, correct. Okay, now that also makes sense because the output dimension depends upon the dimension of v. What is the output dimension? It is also 4, right? So that would be the output dimension of your head.
Okay.
Okay, yeah, so that's what we are doing here. Now suppose we take this attention block inside a transformer encoder layer. Assume we apply add and norm, that is their norm on x plus attention of x. So output of attention plus the x, then which statement is true? Okay, layer norm normalize across the feature dimension or across the batch. Which one is true? Layer norm normalize across which dimension? Batch or feature? Hello?
A feature?
Yeah, correct. Okay. Now from the formula, it is also clear that residuals is applied before you do the layer normalization. Okay, and the layer normalization forces the output mean to be 0 across tokens. This is also not necessary. Okay, as first of all you are doing the layer normalization across the features, so there's no need that it has to be mean to be 0 across tokens or across the batch if you have. Okay, yeah, so that's all. Yeah, now for your practice assignment question, if you go about it, it has your model embedding dimension is given to you. Okay, that you are starting off with dimension embedding of 12. Okay, then what does your question say? That your encoder uses 3 attention heads. Okay, they are all of equal dimension. That is, the output of each head is t times dk, where t is the sequence length and dk is the output dimension of head. So each of my model uses, oh sorry, each of my head outputs in t cross dk, and they are of equal dimension. So what should be the value of dk then? We have 3 heads, each of equal
4.
dimension. 4, correct. Okay, so you have 12 dimension embedding. You are passing it to 3 heads. Okay, and after that you have to do the concatenation, of course. So that's why each of these heads should be output in 4 dimension. After computing or output of all of the heads, they are concatenated to form a vector of dimension 12, okay, which is then multiplied by an output projection matrix WO for n in computation. Okay, and there are no biases in the projection matrix. Projection matrices have the same shape. So WQ, WK, WV also has the same shape for all the heads. Okay, so WQ is also T cross. It's not T cross D. It's D cross DK. WK is also T cross DK. WV is also D cross DK. D here is my 12. DK we have already figured it out. It would be 4. Okay, so each of my these three matrices is of dimension 12 cross 4. Is it clear till now? How these matrices
Yes,
are of
sir.
dimension 12 cross 4. Now, these are some observations that query projection has 144 learnable parameters, and the feed-forward neural network that you use after the concatenation has one hidden layer, and hidden layer size is half of the model embedding dimension. Model embedding dimension is 12, so it will be 6. Then ANN includes output layer as well, and final output projection, including all parameters for ANN, has only 144 parameters. Using this, you have to mostly figure it out the shape and size of WQK and the total number of parameters. So we have already figured it out what will be the size of WQ, WK, WV. Okay. Now, what should be the size of WO here? Oh, sorry, not the WO, the output projection for this ANN. We will be having the output that would be of T cross 12. Okay, that will be feed into a feed forward neural network in which there is one hidden layer which is half of the size. So there will be two matrices associated with this, right? One would be between the input and the hidden layer, and one would be the hidden layer and the output layer. So what should be the size of those matrices? Okay.
12 into 6.
Yeah, correct. And what about the second one?
6 into 12.
Correct. Okay. Is it clear for everyone why it would be 12 into 6 and 6 into 12? Okay. Yeah. So
So
once you know the
how
size,
second one was 6 cross 12?
see the feed forward neural network that we have, it uses one hidden layer, okay, and the hidden layer size is half of the embedding dimension. Okay, so our model dimension here is 12. Okay, so hidden layer size would be 6. Okay, so how this if I show in the visualization here, okay, so how it's these things is working, we have this our input that will feed. Okay, this input is of size T cross 12. Okay, as our D model is of size 12. Okay, now this is the output after like you do the concatenation and the projection. Now this is the output that you are going to feed it to the feed forward neural network now. Okay, in this feed forward neural network you have one hidden layer. Okay, and that hidden layer size is half of this input dimension, that is 6. So it would be 6 dimension, so maybe I can mention it as pp 6. Okay, so it is an R6. Then what you do, you are again going to project it to the same dimension. That's the typical architecture behavior for our any transformer model. That after passing the network to the hidden layer, okay, you project it into the same dimension. Okay, so things will work like this. You have your uh, input that will go from uh, dimension 12 to dimension 6. Okay, and it will again go from dimension 6 to dimension 12. Okay, that's how the architecture of neural network was designed, right? Okay, so
Yes,
that's why
sir.
here it would be 6 cross 12 and 12 cross 6 and 6 cross 12. Okay,
Okay, sir.
yeah. Okay, once you know this dimension, okay, using this observation, you will be easily able to calculate the total number of parameters. Okay, yeah. So that's all I have for today's session. So anyone has any more doubts, can ask.
What are we going to discuss on next Monday?
Next Monday, most likely we'll be covering the week 11. Okay. You want anything else next Monday?
Uh, if you can, some simple codes for RNN architecture for NPPE2. I asked Sciencer also, requesting you also to have any one of
Uh,
you.
for NPP2. So when is next Monday? 6th, 7th. Oh, sorry, on 8th is the next Monday. So simple RNN code. When like we can do that, no problem in that.
Is week 11
So with
heavy?
respect, week 11 is little bit heavy as it has vision transformer plus the diffusion model. So the coding wise, it is not heavy. Coding wise, I would say week 11 is the simplest one. Okay, there's 2 3 lines of code is there in the week 11. But theoretical wise, it is more heavy. So if I have to cover this part, then RNN part will can cover. Okay, I will try to cover RNN. Okay,
Yeah,
I will
thank
send
you.
some code snippets. So you mainly want around like the structure, like or the
Yeah,
training
the
flow.
basic structure, how to get a flow,
Okay,
because
okay,
in coding sessions also we are discussing only the codes which are there in the lecture slides.
okay, okay. Got it.
The
Okay,
simplest form, yeah,
okay. Any simplest form you want? Okay,
yeah,
so uh, then I will just choose one. I will not go into the some data set then. Will that work?
yeah, no problem.
Okay, I will just choose one two simple examples and maybe on that example I will do that. Okay. Otherwise, again, if I go into do the training on the data set, then again it's kind of will become same. If you just want to understand the flow, then I think on one two simple
Yeah,
example, then it will
that's
be
enough. That's enough.
okay. Okay, yeah. Anything else? Okay. So then that's all for today. Thank you guys for joining. Please fill the feedback form. Uh, See you in the next session. Good night, everyone.
Thank you, sir. Good night.